All right, final section of chapter 3. Going to be looking at compound interest mainly. Formula commonly used for compound interest looks like this, so you can see why it plays into this chapter. Obviously fits the model of our exponential functions. In looking at this, remember that this is always represents the initial amount. This is our rate of change, rate of growth, or decay. Then of course we have our exponent, typically in terms of time. So when you're looking at this one of the main things is to recognize is this represents your present value. So if I'm investing money, which is typically what we're talking about with compound interest, then this is the amount that I am starting with. This is the amount that I am ending with. This is my future value. Sometimes you'll even see these in formulas as FV and PV, right? Future value, present value. R is your interest rate, and T is time. So let's take a look at one here. So if I invest $5,000, 6.5% annual interest, how much will you have if the interest is compounded either annually or monthly? So here's the idea. We are starting with $5,000. This is our principal, our starting amount. We're investing, so this is growth. This is money that we are earning, so 1 plus the rate of 6.5%. We're going to write as 0.065. So here's what K represents. K represents the number of compoundings per period. Notice that this is an annual interest rate. That's important. That means I am getting this much interest per year, right? Once per year. So if this interest is being compounded annually, right? So how many times would that happen per year? That's what K represents, is how often is your money being compounded. So if this is an annual interest rate and my money is being compounded annually, meaning once per year, then that means my K would represent 1, right? So it's only going to happen once per period of compounding time, right? So annually is going to happen once per year. So this K is also 1. And then T would represent the number of years that we're going to be doing this for. So if we're just going to keep it generic to represent any number of years, we would just write T as time. But let's just say, but I want to know how much money, if I put $5,000 in and, I want to see how much money I'm going to have in 5 years from now. Well, I'll just plug in a 5 for T, and that will tell you how much money you have in 5 years. And remember, in this problem particularly, T represents years because we're dealing in an annual interest rate. So that's our T is going to match how often our interest rate is being applied. So if I said 1,000 as my principal times 1 plus my rate divided by 1, so 0.065. Don't have to divide that by 1. Nothing's going to change there. And then I'm going to raise it to, so if I want to know how much money I'll have in 5 years, put in a 5. Here's the amount that would now be in my account. So if you look at it this way, how much interest did you make? If you started with 5,000 and now you're up to this, so that difference, the $1,850, is the interest that you earned over those 5 years. So kind of leaving it in terms of T allows you to apply any number of years you want to apply it to. So what if it was monthly? So what if it was monthly instead of annually? So my interest is going to get compounded more often this way, so I should make more money if we do this right, because I'm getting interest more often. If it is monthly, then remember the way we want to look at our value for K is how often does it happen per year. So if this is an annual interest rate, but it's being compounded monthly, K represents my number of compounding periods per year. So if it's monthly, that's going to happen 12 times per year. So what the bank would do is they would take your interest, break it up over 12 chunks, since it's monthly, and they are now applying that more often, right? So it won't make a huge difference, but if they're going to apply it sooner, like at the end of each month, rather than all of it at the end of the year, then I should be making more money off of this. So let's do the same compare it to the same answer that we just did. So now we're going to do our 5,000 times 1 plus, we have our rate over 12. But now our exponent is, if we're doing this for 5 years, is 12 times 5, so 60. So you can see I'm making a little bit more money, right? I made like an extra 64 bucks just because it was compounded more often. So the more often it's compounded, the more money you're going to make, right? And stuff like this. So let me jump you down to this one, just one extra one here for some practice. I wanted you to see a little bit of this wording too. So I got 800 to invest. That's my initial amount. So that's how much our principal is we're starting with. What annual interest rate, if I'm being compounded quarterly, is required for me to double my money in 10 years. So they are saying, we're not going to tell you what your interest rate is. That's what we want you to figure out. This is being compounded quarterly, so how many times would that happen per year? Because this is an annual interest rate. So how many compounded periods per year, right? So quarterly means this would happen 4 times a year. They did tell us it's going to be 10 years. So I'm looking at this. So what goes over here? Right? Well, in this case, I'm looking for my money to double. So my 800 is going to become 1600. So that's my future value. And now I just have to use some basic algebra to solve for R. Guys, don't forget on this. I know you know this, but I'm going to remind you anyway. Would I need logarithms to solve an equation like this? I don't, right? Because I'm not solving for an exponent right now. This is just going to be basic algebra, right? I'm going to divide my 800 over 1600 divided by 800 is 2. Guys, which, by the way, you really could have gone straight to this step right away once you start doing these, because if I'm looking at doubling my money, then this will always be double what I start with. And if I always take the first step of dividing this over, I would always get 2 no matter what amount I'm starting with, right? So you really could jump straight to this step. 40 is my exponent. So how do we get rid of the 40? I need to take the 40th root of both sides. Going to be a pretty darn tiny number. So let me take the 40th root of 2 on that one. So that gets rid of the 40. And I'm not going to write all this out from my calculator. I'm just going to do this. 40th root of 2 is equal to 1 plus r over 4. So that puts you here. So subtract the 1, multiply by 4. So subtract the 1, multiply by 4, and here's my interest rate. So about 7% would be the interest rate we would need in order to double my money in 10 years, if it's compounded quarterly. So that's what we're seeing on this one. All right, let me keep it moving for you. Got a few pages to go through. One thing we can do on this, and this is why I wanted to show you this one, is we can use our calculator. We've done this before in order to solve. So we can use logarithms, or like we did at the beginning of the chapter before we covered logarithms, we could use our calculator and solve that way as well. So for this problem, they're giving you the starting amount of 600, starting with 600 bucks. We want to know, when will my 600 turn into 2400? So my future value is 2400, 8% interest rate, compounded monthly. And so we're wanting to know how many years, right? So we're solving for time. You could use logs to solve for time. We've already covered that. But we could also graph this. And so here's how we would do it graphically, right? Just like we've done before. Right? I'm going to graph 2 equations. I'm going to graph 2400 as one graph. And I'm going to graph this as a separate graph. That's the growth curve, right? This one is my 2400. And so what we're looking for is, when will they intersect each other? So, we go into calc, we choose intersection. I'm looking for that point of intersection. And so this one is saying it would take about 17.4 years, because that's what t represented. About 17.4 years in order for my 600 bucks to turn into 2,400 bucks. Right, so that's about what we're looking at. Let's try one. So if you want to give this guy a shot on your own, great time to pause and give it a try. So for this one, starting with $1,000, 7%. I want my 1,000 bucks to turn into 1,500 bucks. So that shouldn't take too long. That's not a huge change. So here's my future value. Here is my present value. I got my 7%. On this one, it does say monthly again. So that's why my K value is 12. So here's our setup. I could just go straight into the graph. If you wanted to, you could actually divide the 1,000 over first and then graph. With the new equations, be some easier numbers to work with, but that's okay. We'll go with the big guys. So we're going to be graphing 1,500 as one graph. I got my other info as my other graph. So there's my two graphs. Clearly, if I have a graph like y equals 1,500, I'm going to have to get my window much higher to cover that 1,500. My x's are probably okay. Let's just say 2,000. Give us a nice big window to look at. So I should see an intersection in there. So here comes the growth curve. So there's that point of intersection. I want to know what that x coordinate is, because that's time. Which reminds me, that was not k, that was t. K was 12. Anyway, go under calc, choose intersect, enter, enter, enter. So about 5.81 years is what we'd be looking at. So we could certainly use logarithms instead, but we can take advantage of that calculator sometimes. So guys, before I show you this next one, we're actually going to jump to page 301 in your book, and then we're going to take a look at this one. So what we're looking at on here is some explanation of something called annual percent yield. You've probably heard of an APR, an annual percentage rate. That's just simply the annual rate that you're given for, say, a loan or investing or something like that. We typically hear what an APR is, but once in a while you also hear something in terms of an APY. So what's the difference? Annual percentage yield is great to know for comparing one investment to another. If you walked into a bank and they said, and I'll just use this as an example. Let's say you're going to invest your 2,000 bucks, and they tell you, one bank says, well, we're going to invest your money at 5.15%, but we're going to compound it quarterly. Another bank says, well, we're going to invest at 5.2%, so a higher rate, but we only compound it annually, once per year. How do you know what the better deal is? This one is a smaller rate, but it's being compounded more often. So how do I know which one is going to give me more money? So if I really wanted to compare apples to apples, in order to compare investments, and this works with loans too. If you wanted to compare, let's just say one bank is offering you a mortgage loan, like a house loan or even a car loan, and they're saying, well, we're going to give you $15,000 for your car, but they give you one interest rate compounded every so often, and another place offers you a different loan at a different rate compounded for different periods of time. How do you know which one's better, right? And so that's the whole purpose of comparing using an APY. So here's the extra step. The right side still looks like it always has looked, right? Here's what I started with, my 1 plus my rate divided by my compounding period. So if it was quarterly, we're dividing by 4, right? So is this one here, that's my K value looking like this. On the other side, where we would have the A, or the future value, on the left side, they're putting your principal times 1 plus the rate, right? That's our X value that you're seeing on this. So this rate that we are solving for is what it's going to tell us is if you were to take this investment rate compounded quarterly, how would that look if I just gave you the same a rate, but I did it once per year? So if I can convert every investment opportunity to just figuring out here's what they're really giving me as a rate once per year, now I could compare apples to apples. Okay, and so that's what we're finding out here. That's what this X represents. It represents the annual rate compounded once per year, right? And so now I could compare this to other things if I took the same approach to their loan or their investment opportunity, right? So as they go on to solve this, they figured out that this rate, 5.15 compounded quarterly, is the same thing as getting 5.25% once per year. And now this APY, I could now go to compare other investment opportunities. If I converted all their stuff to an APY as well, it would tell me which one is the better loan or the better investment opportunity. Let's try that. So I know this is the same problem, but I wanted you to not only have it for your notes, but I also always want you to be able to go through this from start to finish on your own just to make sure you're good with it. So here's our principal. We're getting that rate of 5.15 compounded quarterly. Tell you what, just to make things exciting, what if it were monthly? We'll make it a little different than the book's problem. So we're going to compound this monthly instead of quarterly. Let's see what that does for us. So it should change the answer a little bit. So what would be the equivalent annual percent yield on this one? So future value, remember this is what we're putting in for that future value. Understand that T goes away in this setup because I am converting this to an annual percentage yield. It's once per year. So that's like T is 1 because 1 year is going to go by for us to figure this out. So that future value, I got my principal times 1 plus X. So it looks like that on the left side. That's our future value. On the right side, I have my initial $2,000. We have our rate being offered. If we change this to monthly, my K is now 12. So he's a 12 and he's a 12. We leave T as 1 for what we just talked about. So this is the equation I'm now solving. And remember, you don't need logs for this, right? Because I'm not solving for an exponent. I'm just using basic algebra here to solve this. So certainly one thing I could do would be to divide both sides by that 2,000. So that part can really go away in this process because that's always going to happen. So if you start recognizing some of that, we could kind of skip to this next stage. I'm just going to throw all that in my calculator here instead of rewriting it all. I need my parentheses since I have the exponent, so 1 plus 0.0515 over 12, and all of that is being raised to the 12th power. And so all I'm going to do is subtract 1 from both sides to get x by itself. And so here's our new rate, 5.27%. So you'll notice this created a higher APY because we were compounding it more often than the book was. They were only doing theirs quarterly. We did ours monthly. So we compounded this more often, which gives you a higher APY. So in other words, if you were out shopping for a loan or if you were looking to invest money, the best way to compare products would be to look at their APY values instead of the APR, right? If my APR is 515, but it's being compounded, it would be hard to compare to a different product if I kept it in these terms. But if you convert it to the APY, annual percentage yield, now you can put everything onto common ground in order to compare values. Let's keep it moving. Compounding continuously. So this is, you would actually see this on the same page of the book where I just was, 301 I think it was. So for this formula, So that one's right here. So they do the example here. The formula must be on the previous page. I already have it written into the notes, so that's fine. So on page 300 down here is where you'll see the explanation for compounding continuously. Here's the formula that we are using. So here's something I really want to point out to you. You can only use this formula when it is being compounded continuously. If you are given a certain number of times of compounding, you have to use this formula. So keep in mind which formula you're going to be using. You'll only use this one if you literally see the words compounds continuously. Then this is the formula we're going to be using. All right, so what I'm doing on this one is you could solve this in a couple ways. We've already looked at how you can solve equations like this using logs or natural logs in this case. Totally fine if you go that route. I'm going to show you something on the calculator as well. So our principal, still future value. So my principal is $200. And it's being compounded continuously. So we're throwing into this formula. So find it at the end of certain periods of time here. So for the rate on this one, we have 7%. And they want to know what is my future value after 1 year, 2 years, 3 years, 4 years, 5. So I could find all those. But if I really wanted to find multiple years like that, I would have to solve this equation. If I was going to do logs, I'd have to solve it like 7 different times in order to get those seven years, right? To see how much money I'm going to be looking at each year. So something we could take advantage of in the calculator for this is just to graph it and look at the table. If it said only, and this is what I was talking about over here, if it gave me only one value, like if it just said, okay, so how much money are you going to have after 5 years? Just plug in the 5 and do it that way. Don't graph it. But in a case like this where I need multiple answers, I don't want to do this a bunch of times. So I'm going to do it in one shot by graphing. So I'm going to do my 200. I got an extra 0 in there. So I got my 200 times e to the 0.07x. So I'm going to graph it. I'm not even looking at the window at this point, though. I'm going to go to the table of values. So here's what we're taking advantage of. If you go into your table, here's all your info. So the 0 is if time were 0. That's what you started with, $200. After 1 year, this is what you'd now have. After 2 years, 3, 4, so on and on and on, right? So you could do this. And I mean, we could have done this for 1 year, but I'd rather not make the table if I only need one value. I'm only doing this because they were asking me to find 7 values, right? 1 through 7. So I could pull them right off this chart now, and that would be it. That would be all 7 answers. All right, let me go down to this one. You may have heard mention of an annuity. So an annuity, when you start getting into long-term investments, maybe retirement investments, you'd start hearing about an annuity. So an annuity is something that you would pay into for a long period of time. And then when you retire, it's usually what an annuity is for, they would then agree to pay you a lump sum every month for the rest of your life. And typically the way they calculate these things is, let's just say you retire at 62. And they basically assume the average person may die around 80, right? So what they would do is they would figure out your payments from the age of 62 to 80 and agree to say, we're going to pay you back this lump sum every month for the rest of your life. Well, if you die before you're 80, they made money off of you because now they don't have to pay out the rest of your annuity. If you were to live past 80, the longer you live past 80, now you're making money off of them because you only had to invest so much, and they were planning on you kicking the bucket at the age of 80. But if you outlive that plan, they have to keep paying you. That's how the annuity works until you die. So they're going to eventually make money, or you're eventually making money off of them if you outlive their plans. So the reason this one is a little different is because this is not a one-time investment. right? This is something that the person is paying into on a regular basis. So it's not just a one-time principal investment. It's like, well, what if I was investing a certain principal, but I kept putting money in, I kept putting money in, kept putting money in. How do I determine a future value for that? So here's the way they wrote their formula. I translated some of that for you. So the I represents right here, the rate divided by your compounding periods. So it's the same as what we had before, right? And just like their N represents periods of time times compounding periods, that's how we saw it in the previous formula. And then they have this extra piece. A lot of this has to do with you putting in regular investments, not just a one-time investment. So anyway, so this is basically what they're looking at. So it's not a ton different than the formula we've already looked at, but it has this and this being thrown in to deal with this new scenario. Okay, and so if you can kind of put it in this terms, maybe that would be easier for you to remember rather than the way that they have it written here. But let's throw in some numbers so we can see how this works out. So what is my future value? So we're starting, our principal investment is this $400 that we're putting in. Try to write small. I got the 1 plus my rate over K. So that's the 0.0775 over K. This is quarterly, so it's for K would be 4. And then 4T goes up top. So that's this guy right here, right? So it's your compounding periods for 25 years. So this is going to happen 100 times. I got the -1, and all that is being divided by R over K, which is this value right here. And I'm not going to have room right there, but that's okay. So my R over K is again the 0.0775 over 4. So it looks something like this. A lot going on there. Let's see if we can put that into a calculator and see if we can come out with the same thing they came out with. So I'll save you some time here. I already put it in. So here's the answer I came out with. It's a little different than theirs. I'm pretty sure theirs is wrong. I looked up theirs in their book, and they have the exact same setup that I do, but they came out with the 120. So it looks like I would say theirs is wrong because I went over every step in this, and this is what it should come out to be. So again, this person now has this amount. So if this is the amount she has in there 25 years later when she retires, they would then base her monthly payments off of this number for the rest of her life. And so that's how she would get paid out for the annuity. Let's move on. And here's our last one. So calculating loan payments, something you should all know about for sure. And let me take you to page 303 real quick so you can see our formula we're working on with this one. So if you go down to the bottom of page 303, they describe this formula as the present value of an annuity. So an annuities all come back to just having like lump sum payments over a period of time. So that if you're looking at calculating a payment for a loan, you're now making those payments, those lump sums starting now. So they call that basically the present value. It is almost the same formula that we were just looking at. You'll notice this is a negative exponent and it is 1 minus instead of -1 back here. So some couple changes in this, but let me show you. Let's just walk through one here together so you can see this. But not a whole lot of difference to this. The value for I is still your interest rate, the APR, right? So 3.1, so they wrote that as 0.013, divided by however often you are making these payments. So typically it's a monthly payment, and so that's why it's the rate over 12, right? Real similar to what we saw in the last problem. What we're trying to calculate on this one is this guy. So there's a little twist to this one where we're not looking for how much is being paid over time. We are looking for how much are my monthly payments going to be, right? That's what someone typically wants to know. If I walk into the dealership and they tell me the car that you want is $19,000, and you say, okay, well, I can put $3,000 down, so I only have to take a loan out, I only have to finance $16,000. So what are my payments going to be? Right? That's like what the question person would ask. So here's how it gets calculated. Right? So this R represents your monthly payments that we're trying to solve for. So again, you have your rate over how often you're making payments. Same thing down here. We have technically the present value of the car on this case, because we're doing a loan instead of making an investment. So we have the present value of $16,000 because it was $19,000, but we gave them $3,000 as a down payment. So this is all we have to finance, is the $16,000. Right? And so again, you see the stuff going on up here. You have your time. So this person agreed to pay it for a 3-year loan. Typically it's 5 or 6 years, but this one they wanted to do a 3-year loan. Maybe they get a better rate if they do that. So they're doing it for 3 years. So you got -3, and they're paying over 12 months a year. So they're going to make total 36 payments, right, in this 3-year loan. So that's where all these numbers are coming from. From there, solving for R is going to be very basic algebra in solving for that value for R. So it's basically, I got to figure out this whole number and divide it into my 16,000. And that's where they came up with these payments. So if the person makes the payments for the next 3 years, then their car would be paid off. And that's it. So that is the end of chapter 3.